Hi everybody. Let's practice with the diagonals, angles and diagonals of a polygon. This, this exercise starts off talking about a pentagon and talks about the angles. And I'm sure this meant to say that the angles are in the ratio of 2 to 3 to 4 to 5 to 6. Show the processes you find the measures of these at 5 angles. First thing you'd want to think is, what are the 5 angles of a pentagon add up to? And you have to remember this formula. N minus 2 times 180 equals the sum of the interior angles of any polygon. The sum of the interior angles. So with a pentagon, that'd be 5 minus 2 times 180, which is going to give us 3 times 180. And you play with that for a second, but that's going to be 540 degrees. So I know the angles of every pentagon are going to add up to 540. But in this irregular pentagon, all the angles are different. They're in the ratio, the angles are in the ratio of 2 to 3 to 4 to 5 to 6. So I'm thinking that 2x plus 3x plus 4x plus 5x, you've got a plus sign there, plus 5x plus 6x ought to add up to 540. That is the sum of the interior angles for every pentagon. We'll just clean up this left-hand member. I see 5x there and 5x there and 10x here. I think I got 20x altogether. You check it too, though. And if 20x is equal to 540, let me divide both sides by 20, and I'd figure out that x is equal to 27. Now, if these things are in this ratio, I know that I can evaluate them this way. 2 times 27 would be 54 degrees. 3 times 27 would be 81 degrees. 4 times 27 is 108 degrees. 5 times 27 would be 135, I'm pretty sure. And 6 times 27, let's see, that'd be 120 and 42, 162 degrees. These would be the interior angles of that irregular pentagon, whose angles are in a ratio of 2 to 3 to 4 to 5 to 6. It says here, sketch a regular hexagon. I'm going to pause and do that. So I made a sketch of a regular hexagon, A, B, C, D, E, F. How many diagonals can be drawn in the figure? Well, that's really just a formula. I would first think, how many diagonals can you draw from a single vertex in this 6-sided figure? And I can draw 3 diagonals from a single vertex. And how many vertices you got? Well, I got 6 vertices. So it makes me think 6 times 3 would be 18 diagonals altogether. But I don't want to count anything twice. So actually, I'm pretty sure there are just 9 diagonals in there. I got 3 times 6 to be 18 divided by 2, so I declare there to be 9 diagonals in this figure. It'd be fun to draw, but I got other stuff I got to worry about. What is the sum of the interior angles? And I really need to go back to this formula, n minus 2 times 180. That gives me the interior angles of any polygon. And in this case, since it's a 6-sided polygon, that'd be 6 minus 2 times 180, which is going to give me 4 times 180. And I happen to know that that's 720 degrees, 4 times 180. So all the interior angles of this polygon would add up to 720. Give the measure of each interior angle. Well, I know all the angles add up to 720, and if this is truly regular, they all be the same size, so I should divide that by 6. And that would force, when I'm doing 720 divided by 6, that'd be 120 degrees each. That would be the measure of each interior angle. But you might have thought about this. What if I extended aside? How big would that exterior angle have to be? And we should be thinking, well, the exterior angles add up to 360, all of them would. And they're all 6 of them would be the same size, so if I divided that by 6, each exterior angle would be 60. And it's pretty easy to believe if that exterior angle is 60 right there, that the interior angle would be 120. So I'm happy with that. And then I can multiply that 120 times 6 and I get this 720. I know the sum of the interior angles. Let's play some more. The sum of the interior angles of a regular polygon is 1440. How many sides does this polygon have? Gotta go back to that formula again. N minus 2 times 180. I'll set the formula for the sum of the interior angles, n minus 2 times 180, equal to the sum of the interior angles. Equals 1440. to think, well, what do I got to do to solve this equation? Should I multiply the 180 through the parentheses? You could, and it would work, but I don't think it's the best idea. I think I ought to divide those sides by 180. And that better go cleanly on the right-hand side. I think that it will. Here, the 180 is going to fall off. I'm just left with n minus 2. Here, I can knock a 0 off of each one and divide 144 by 18. And I know that's going to be 8. So if n minus 2 is equal to 8, then n must be 10. So over here, how many sides has it got? I got 10 sides. I got a decagon, huh? He exclaims, he's got a decagon. Give the measure of each interior angle and the measure of each exterior angle. Let me think about that decagon for a second. And I think I'm going to do the exterior angle first. I know that the exterior angles add up to 360. And in a 10-sided figure, there have to be 10 of them. So each exterior angle would have been 36 degrees. And if you think, well, there's some polygon over here, I'm not sure exactly what it looks like, but I know this, stand aside, this exterior angle would have been 36 degrees right there. How big would the interior angle have to be? And it would have to be the supplement of 36 degrees. So the interior angle would have to be 180 minus 36 would be 144 degrees. That's kind of a nice way to solve that. I'm sure you could have used another formula, but I'm sure that that will also work. Let's play some more. Oh, sorry about that. Now, we're given expressions for the 4 angles inside this quadrilateral. And it tells me to write the good equation and find the measures of those angles. Now, if these were the angles of a triangle, we'd add them up to 180. But since they're the angles of a quadrilateral, we got to think, well, what do the angles of a quadrilateral add up to? You could go back to n minus 2 times 180. Or you could remember that they add up to 360 degrees. So I know that these angles would have to add up to 360. Let's hit that equation. 2x minus 8 plus 3x minus 6 plus, ooh, I forgot that one too, plus x itself, I'll put that first, plus the last angle, x plus 10, should add up to, what do the angles of a quadrilateral add up to? To 360. And then we'll gather like terms. I see 5, 6, 7x right there. I got a negative 8 and a negative 6. There's a negative 14, but a positive 10. Negative 14 and a positive 10, give me a negative 4 right there, is equal to 360. Got to solve that little equation. I think I should add 4 to both sides, and that would leave me with 7x equals to 364. I'm going to divide both sides by 7 and see what happens. 364 divided by 7. And I'm going to hit that with a calculator. Maybe I can make that happen and make it so you can see it. I'd like it if you could see it. Let's do with that 360 divided by, oh, no, sir, that was 364 divided by 7. And that's 52. I'm glad it came up as cleanly as it did. X is equal to 52. So now I've got to figure out the measures of all those angles. I guess angle L would have been 52 degrees. Angle M would be 2 times 52 is 104. Minus 8 would be 96 degrees. And angle J would be 3 times 52. I think that's 156. Minus 6 would be 150 degrees. Then angle K would just be x plus 10. Therefore, 52 plus 10 would be 62 degrees. You can check me on that if you want to, but I'm pretty sure those add up to 360. They'd better. Playing some more, talking about polygons. Check the exterior measures of the angles in this quadrilateral. Give the value of x and the measure of each interior angle. And what you would be thinking is the exterior angles of a quadrilateral always add up to the same number, and in fact they always add up to 360. So we have an equation that we could write. X minus 11, we're just going to sum all those up. X minus 11 plus x plus 10 plus 2x minus 42 plus that last angle, 31 degrees, should add up to 360. I know this because the exterior angles of every every polygon in the world add up to 360. We'll gather like terms. 2x. I got 4x there, don't I? And I have a, let's see about these constants. I have a negative 53. Put that on the side. I don't want to screw this up. I have a negative 53 and a positive 42. Oh, that's just a positive 41, isn't it? Excuse me. And a positive 41. And that is the difference of 12, doesn't it? So I think I got 4x, and that should be minus 12 is equal to 360. I would add 12 to both sides, and I got 4x equals to 372. Man, I got a calculator. I think I could probably do that in my head. It might be about 93, but let's see about that. If I took 372 and divided it by 4, yep, 93 degrees, or 93 is the value of x. I'm not sure about degrees. So let me go around here and figure out about these angles. This angle would have been 93 plus 10, that'd be 103. This is 93 minus 11, that'd be probably 82. This angle's 2 times 93, about 186, minus 42. Oh man, 186 minus 42, I'm going to hit that with my calculator. 186 minus 42, that gives me 144 for this angle. And this angle's just 31. But it asked me the measures of the interior angles. I don't think that's going to be a problem once we got the exterior angles. How about the interior angle here? It's got to be a supplement of 103. That's got to be 77. I'm going to list the interior angles right here. And this, the exterior angle at 82 here, what about the interior angle? It's got to be the supplement of 82. That'd be 98. And if this angle's 144, what about that interior angle? Looking for the supplement of 144, that'd be 36. And if this angle's 31, what about that angle? Well, they're adding up to 180. I'll take that 31 out of 180. I guess that's going to leave me with 149? Yep, I think so, 149. That's what I think each interior angle would have had to have been in this polygon. It's an irregular one, isn't it? And then I look at this last question. One more thing to play with. If each interior angle of a regular polygon is 156, how many sides has it got? Now you could work that with a formula, but I would tell you, if the exterior angles, if the interior angles are 156, how big are the exterior angles? If the interior angle is 156, the exterior angle is going to have to be the supplement of that 156, and that would be 24 degrees. So I got the exterior angles to be 24. But I know the exterior angles add up to 360. So I always think, well, how many 24s could there be in 360? And that's got to be 15, I believe. 360 divided by 24 is 15. So it's got 15 sides. Give the sum of the interior angles. Well, if it got 15 sides and they're all 156, that'd be 156 times 15. That's a good thing to hit with the calculator, I figure. 156 times 15. So that had to be 2340, 2,340 degrees for the sum of the interior angles. 2,340. How many diagonals can be drawn in this figure? Oh, Lord. Well, I got to remember, it's got 15 sides. So how many diagonals from a single vertex? I'd have to leave 3 of them out. So I think if it's got a 15-sided polygon, I can draw 12 diagonals from a single vertex. 12 diagonals from every vertex. I got 15 vertices. I don't want to count anything twice. This will tell me how many diagonals I got. And I can multiply 12 times 15. That's 180. Divided by 2 would be 90. Or you could have divided 12 by 2. It would have been just 6 times 15, but still gives you 90. So you could draw 90 diagonals in that 15-sided figure. That's a bunch of clever thoughts, huh?